See, this is the topic we are going to cover today. Dimensional analysis. I will tell you the fundamental aspect of dimensional analysis, and I'm trying to solve a question also by using this mathematical technique. Dimensional analysis is actually the method of dimensions. It is a quantitative technique, that is mathematical technique, involving dimensions of physical quantities. You know that the fundamental dimensions of physical quantities usually we come across, that is of mass, length, time, and temperature. They are M, L, T, and theta for the temperature. M for mass, L for length, T is for time, and theta for the temperature. So these are the fundamental dimensions we come across, out of which in a typical fluid mechanics problems, the temperature part may not be involved. So basically we'll be using the three fundamental dimensions, M, L, and T. Previously, so we have written down the dimensions of various physical quantities, the basic properties of viscosity, density, etc. How to give the dimensions of those physical quantities. For example, density is mass divided by volume, and its dimension then will be m divided by L cube. So ml raised to minus 3. So we know in that way, so we know the fundamental dimensions as well as the derived the dimensions derived out of these fundamental dimensions. Okay. And also we know the dimensionless groups or parameters. Dimensionless groups or parameters, basically the important dimensionless numbers, unitless numbers, or quantities which we use in fluid mechanics. The most important ones are Reynolds number, Prout number, Weber number, Euler number, Mach number, etc. So these are all prominent dimensionless groups or parameters used in typical fluid mechanics problems. So this dimensional analysis that involves two methods. One is Rayleigh's method, and the other one is Buckingham's Pi method or Buckingham Spy Theorem, popularly known as Buckingham Spy Theorem. Rayleigh's method is very simple one, but it has got its own limitations. When number of variables or fundamental quantities involved in a physical phenomenon are more, number of variables involved in a typical problem are more, say more than 4. Rayleigh's method may not be suitable, even though we can use it. But Buckingham's Spy Theorem, when you use that, so we don't have that kind of limitations. So we can use as many number of variables as you like. Then what is the use of these dimensional analysis? See, basically, this method is used to obtain the functional relationship between the variables involved in a physical phenomenon. For example, the pressure variation in a pipeline flow. So you want to study the pressure variation or pressure drop that is occurring in a turbulent, let us say turbulent flow in a pipeline. So what are the influencing parameters or variables associated with that fluid flow problem? So if you analyze that, the researchers will be finding out the various variables or the physical properties governing this particular problem. That is, the problem is to find out the pressure drop in turbulent flow through circular pipe. The pipeline diameter, let us say D, and pipeline length, let's say L, and the fluid flowing through the pipeline, let it have dynamic viscosity mu, and pipe roughness, the microscopic projections on the surface. So quantitatively, we express it as roughness of the surface of the pipe. So it may be denoted by epsilon or say the letter K. So pipe roughness K, pipe length L, pipe diameter D, and pipe the other fluid properties like viscosity is mu, and fluid density, that is rho, and average flow velocity V. So if we use these variables mu, V, K, then this D, L, all these basic these variables involved in this problem, and try to connect with the pressure drop occurring in the flow when the turbulent flow proceeds through the pipeline, then we can arrive at a functional relationship using this dimensional analysis. So let us make use of Buckingham Spy Theorem for this purpose. So that is a simple one to understand, and it can be used when number of variables are more. So when Rayleigh's method is used, so we have the restriction in the number of variables. Okay, so when number of variables is more than 4, then Rayleigh's method will not be so adequate, even if you can make use of it. But the Buckingham Spy Theorem doesn't have that constraint. So let me tell you what is this Buckingham Spy Theorem. See, this is that classic statement of Buckingham Spy Theorem. If there are n variables involved in a physical phenomenon, and if m is the number of fundamental dimensions used to represent those physical variables, then there can be n minus m dimensionless groups to express the given physical phenomenon. Okay, and this physical phenomenon can then be represented by these dimensionless groups, and the number of dimensionless groups will be n minus m. Okay, it's a number, and the dimensionless groups are known as these pi terms. You know, these dimensionless groups are known as, they are called pi terms. Okay. Then the given physical phenomenon can be modeled like this. For example, let me give you an example straight away. As I told you, the pressure drop problem in a turbulent flow case through a pipeline. So if delta P is the pressure difference in a turbulent flow, so delta P is a function of, this is given, delta P is a function of so many variables, a function of length of the pipe, diameter, then density, then viscosity, then you have flow velocity, say V, average flow velocity through the pipeline, and then the pipe roughness, surface roughness, denoted by epsilon, or the letter say K, that is denoted by say small k, pipe roughness. Okay, so these are the variables on which this pressure drop in the pipe that is occurring in the turbulent flow case through the pipeline that depends on. Okay, so what you can do is, this can be modeled as, so this equation can be modeled like this: a function of, say, another function, let's say phi, a function of these dimensionless groups. Dimensionless groups means, say, pi 1, pi 2, etc. So pi 1, pi 2, pi 3, etc. So now we have to determine how many dimensionless groups are involved. For that purpose, what you should do is, number of variables in this problem. Number of variables in this problem has to be found out. Number of variables influencing the given physical phenomenon. Here the physical phenomenon is a pressure drop. So we have to study that phenomenon. So number of variables here, n, is equal to, so if you count delta P, L, D, rho, mu, V, and K, then total is 7. And out of which dependent variable is 1. Out of which, dependent variable is, which is that delta P is a dependent variable. So now dependent variable is 1, and independent on which this delta P depends on. So independent variables here is 6 variables, which are they? L, D, rho, mu, V, and K. So that is 6. So total we have 7 variables, dependent and independent together. So what you should do is, now the number of pi terms we have to find out. So how do you find out that? So here in this problem, the number of fundamental dimensions required, number of fundamental dimensions required to express these variables, express the variables given, number of fundamental dimensions. See here, if you consider pressure, that is force, normal force per unit area, so that has dimensions, that will contain the fundamental dimensions m, l, and t, and the length, diameter, density, dynamic viscosity, flow velocity, and pipe roughness. See, roughness as a dimension. Roughness means actually the height of the microscopic projections on the pipe surface. So that is essentially has the dimension of the length. Okay, so length itself. So if you consider the variables involved in this problem, you can see that the number of fundamental dimensions required to express this, that is MLT only. The temperature is not required, MLT. Okay, so number of fundamental dimensions which we designate by small letter m, and here that m is 3. So m is equal to 3. Okay, this is important. And the number of variables involved in the problem is 7. And therefore, the next step is number of pi terms, dimensionless groups, or pi terms as specified in the Buckingham Spy Theorem. Number of pi terms will be n minus m. So what is that? 7 minus 3. Okay, so that is 4. So there are 4 pi terms involved in this problem, in this given problem. So what I can do is, this pi 1, pi 2, pi 3, there are 4 pi terms, pi 1, pi 2, pi 3, and pi 4. So these 4 pi terms can fully represent the given physical phenomenon or given fluid flow problem. So function of all these, mathematically, you can write function of all these pi terms, that is equal to 0. This is another way of representing the given problem. Or you can say pi 1 is a function of or. So this can also be written as what? Pi 1, the first pi term, any pi term is a function of the rest. So pi 1 is equal to, say, another function. Say pi 1 is another function of say pi 2, pi 3, and pi 4. So instead of writing function of all the pi terms is equal to 0, you can express like first one pi term is a function of the rest. Okay, so pi 1 is a function of pi 2, pi 3, and pi 4. Okay, like this. So the given problem can be modeled like this. So these let these equations be say 1. Okay, so this is, let's say, 2. So you can express it like this. Now the next step is to find out pi 1, pi 2, pi 3, and pi 4. See, this is that question which I explained to you just now. The pressure difference delta P in a pipe of diameter D and length L due to turbulent flow depends on the velocity, that is in fact the average velocity of flow V, dynamic viscosity mu, density, mass density of the fluid rho, and the pipe surface roughness is K, and using Buckingham Spy Theorem obtain an expression for delta P. See, this is another objective also. Once you get the pressure drop in the pipeline through which the turbulent flow is proceeding, you can even find out the head loss due to friction. So basically, you're finding the head loss due to friction, pressure head drop due to friction. And in that way, you may be in a position to arrive at Darcy-Weisbach equation. So sometimes in the question like this, you will be asked to obtain ultimately that equation, important equation, Darcy's Weisbach equation, for finding the loss of head due to friction through pipelines in a generalized flow situation through a pipeline. Especially here it is for the turbulent flow. Okay, number of pi terms pi 1, pi 2, pi 3, etc. See, in each pi term, now, so let us proceed further. In each pi term, there will be m plus 1 terms. Okay, so that's very important. In each pi term, in each pi term, there will be how many variables are involved. So there will be m plus 1. M is the number of fundamental dimensions, which in this case is 3. So m is equal to 3 here. So m plus 1, 3 plus 1. So there will be 3 plus 1 variables in each pi term, variables, and out of which m number will be repeating. So there will be repeating variables also in each pi term, pi 1, pi 2, pi 3, pi 3 and pi 4, sorry, pi 1, pi 2, pi 3 and pi 4, and out of which some variables will be repeating. So repeating variables, variables that is m number, m. So 3 variables will be repeating. Remember, 3 variables will be repeating. We have to choose it adequately, and non-repeating will be 1. Non-repeating variable in each pi term. Non-repeating variable will be non-repeating variable will be 1. Okay, and out of the 3 variables repeating, see, what is more important is some are representing fluid property, some flow property, and some geometric property. So preferably the basic criteria is one geometric property. So how do you select the repeating variables? So we will choose one geometric property. Okay, the basic thumb rule is this one. Then the second one, we will choose out of the flow properties, we will choose one flow property. Out of the given variables, we have to choose one geometric, one flow property, and one say fluid property. This is a generalized thumb rule. Of course, there are exceptions. So one geometric property. The geometric property here you have length and diameter, and out of which you know that in the case of pipeline flow, even while calculating the Reynolds number, you will be using the diameter. So the prime property, geometric property of concern is the diameter. So you'll choose diameter then. The flow property here, so you don't have to bother about much. The flow property here available is only velocity, so you have to choose that. So velocity. So velocity will be that. Okay, we'll choose that. Then there are two fluid properties here. Fluid properties, of course, that is density is there, kinematic viscosity, sorry, dynamic viscosity mu and rho are there. And one more important thing, see, while choosing repeating variables, normally we will not choose the dependent variable. So here the dependent variable is the pressure drop. So delta P will not be considered while choosing, normally will not be considered, because we will try to avoid the dependent variable while while selecting the repeating variables in the pi term. So out of rho and mu, so which one can you take? See here, it's not the case of viscous flow. So here we are, it's a generalized flow situation where the density is more prominent than the viscosity. So therefore, out of the given variables, now we will decide upon the repeating variables, geometric property as diameter, and flow property as velocity, and fluid property as density. Okay, and of course the pipe roughness is there, and since we have chosen diameter, and we will not choose the pipe roughness now. Okay, so out of all these properties, so the delta P, that you will not consider, because delta P is dependent. So usually we choose the independent properties. Okay, now we'll proceed further. These d, v, rho are the repeating variables. Okay, repeating variables in each of the pi terms. So the first pi term, how do you formulate the pi term? See, the next step is how do you formulate the pi term. So pi 1, then pi 2, second pi term, non-dimensional group, unitless group, representing the given physical problem, pi 1, pi 2, pi 3, and we have pi 4. Okay, so how do you represent it? See, in all these repeating variables will be d, then v, and rho. Okay, in each of them, dv rho, dv rho. Okay, I don't mean to say that you simply take the product, but we will now keep fixed indices for this dv rho. So here again dv rho, and now non-repeating variables, non-repeating variables. You know, one should be there in each pi term. In total, there should be m plus 1, because we have already decided 3 plus 1, 4 variables will be there in each pi term, out of which 3 will be repeating. The repeating ones we have chosen already by using a thumb rule. Okay, so dv rho, and we will add indices, and then we will, in addition to this, now we are going to add, let's say, d raised to a1, v raised to b1, rho raised to c1, and then one non-repeating variable. See that dependent one can be fixed on the first one, can be included in the first pi term. Now d raised to a2, another set of indices, b raised to b2, rho raised to c2, and d raised to a3, v raised to b3, and rho raised to c3. And similarly in pi 4, the repeating variables raised to the indices a4, b4, and c4. And now the other non-repeating variables in each the other pi terms, you know, what are the repeating variables remaining? All have to be used, you know, so that, see, the next what is remaining is the length is remaining. Okay, so the second pi terms here I'm going to include L, and third as a non-repeating variable, and the third one I'm going to use mu, because dynamic viscosity is there. Okay, and now the remaining, the last one, that is the pipe roughness K, so as non-repeating variable. Okay, see, now we have, see, this is the situation now. Now we have the equation. See, pi term, the first one is formulated, and the second pi term. So let me use Roman numerals for that. So this is one, the first pi term, and this one is the second pi term, and this one is the third pi term. This one is the third one, and this is the fourth one. See this? 4 pi terms now ready. And now our effort is to find out this A1, B1, C1. You know, these indices, these are numerical values, and we have to find out. See, once we find A1, B1, C1, A2, B2, C2, A3, B3, C3, A4, B4, C4, and then if we include in this pi terms, the question is over. See, the functional groups representing the given phenomenon, or the non-dimensional group or dimensionless group, will be ready. Okay, so how do we find out? How do we find out A1, B1, C1, these indices? By considering the dimensional homogeneity of each of the pi terms. See, that means the dimensions of various, you know, like if you compare MLT, you know, the indices on both sides, you can equate. You can equate the powers of MLT on both sides, considering the principle of dimensional homogeneity. So pi 1, see the dimension of each pi term. What is the dimension of pi term? It is dimensionless. So dimensionless pi terms. Okay, no dimension at all. So when you represent it, how do you write now? M raised to 0, L raised to 0, T raised to 0, and if temperature is involved, theta raised to 0. So here that will not happen, because we know that the temperature is not involved in this. So MLT, number of fundamental dimensions required here in this problem is just 3. So small letter m is equal to 3. Okay. So m raised to 0, L raised to 0, T raised to 0 is dimension of each pi term, means dimensionless. And on the other side, now the problem is each variable, your objective is to find out the variable and the corresponding dimension. See, in one of the previous classes, you know, I have written down the dimensions of most of the fluid properties, flow properties, geometry properties, etc. You know, that is for this purpose. So the length has the dimension length itself. The diameter has the dimension length itself. And pipe roughness K has the dimension length itself. And then density rho has the dimension mass by unit volume. So that is m L raised to minus 3. Okay. And then we have velocity V, average flow velocity. So the dimension, its unit is meter per second. That is L divided by time. So L T raised to minus 1 P. Then we have now viscosity mu. So it has unit Newton second per meter square or kilogram per meter second. That is a conversion of it. So if you use that, it will be m L raised to minus 1 T raised to minus 1. If you use kilogram per meter second as the unit, that is exactly same as Newton second per meter square. So m L raised to minus 1 T raised to minus 1. Then what remains is now delta P, the dependent variable delta P. And it has got dimension force per unit area, force mlt raised to minus 2 divided by L square. So it will be m L raised to minus 1 T raised to minus 2. You should not commit a mistake while writing down the dimensions. Okay, and now what you should do is in each of these 5 terms you have to substitute these dimensions, and then equating the powers of mlt on both sides of each of the 5 terms, you will be in a position to find out the indices a1 b1 c1, a2 b2 c2, a3 b3 c3, a4 b4 c4, etc. Okay, so I'll try. So I'll show you one, and the rest you can manage. So the first pi term, say pi 1. Okay, so I'm going to insert the dimensions on both sides. So what will be the left hand side? The left hand side of pi 1, m raised to 0, L raised to 0, T raised to 0, because it's dimensionless. And on the right hand side, what is pi term? D raised to a1, V raised to b1, D raised to a1, V raised to b1, rho raised to c1 into delta P. That is the the dependent variable in the question. So delta P. So this is the first pi term. Now we try to insert the dimensions. See, the dimension will be now D is L. So L raised to a1. Then dimension of V is L T raised to, see, I'll put a bracket later. So L T raised to minus 1, that is for V. Then the whole raised to, see, the whole raised to this, whole raised to what? B1. So B1 is the index. B1. Okay. And then the next row is so M L raised to minus 3. And that raised to what? C1. Okay. And what about delta P? So this is actually the product of these terms. And now product into a single term now. So delta P. So delta P will be m L raised to minus 1 T raised to minus 2. That is the dimension of pressure. Here it is pressure drop. Okay, so that into that raised to 1, in fact, because no index is involved in that. So now we got the left hand side and right hand side very clear. And on the left hand side, you simply have, so this is for the pi term. The left hand side, we have m raised to 0, L raised to 0, T raised to 0, and equating the powers of m, L, and T. Okay, so equating, so this is the step. Equating powers of m, L, and T on both sides. Okay, so that will fetch you the dimensions, the dimensionless pi term, pi 1. You will be finding the indices first, a1, b1, c1, and then the pi term. So equating powers of m, L, and T. So if you equate m, so for m, on the left hand side it is 0. So look at it carefully. Left hand side it is 0. Right hand side we have the ml raised to minus 3 whole raised to c1 and into ml raised to minus 1 T raised to minus 2. So what I can write, if you want, I'll group it like this for you, and in that case that will be easy for you, because on the right hand side, see, the right hand side will be somewhat like this. L raised to, if you add the indices, you can write A raised to m into a raised to n is a raised to m plus n. So it is L raised to a1 plus b1, then minus 3c1, then minus 1. So that is for L. So L raised to here it is, see L raised to a1, L raised to here b1, here L raised to minus 3 whole raised to c1. So that is minus L raised to minus 3c1, and then here L raised to minus 1. So finally minus 1. So the indices can be added up. Okay. So using the law of indices, multiplication. Okay. Then what about m? So it will be m raised to what? c1 and m raised to 1. So m raised to c1 plus 1. Then what about the last one? The last one is t. So that is t raised to minus 1 b1. So t raised to minus b1 and final term that t raised to minus 2 is there. That is minus 2. Okay, so like this. So now equating powers of m. So what we get is left hand side is 0, right hand side is c1 plus 1. So c1 plus 1 is equal to 0 and c1 is equal to minus 1. Okay, so that is first index. You got it now. C1. And now the next is equating the powers of t. So fairly t is simple, m is simple, unlike L. So t, equating the powers of t on both sides. So left hand side it is 0, right hand side it is minus b1 minus 2. So minus b1 minus 2 is 0, and if you want to find out b1, you will get minus 2. So b1 is equal to minus 2. Now if you substitute, for the other one, the last one, equating the powers of L for L, that is a1, indices of L on both sides, a1 plus b1 minus 3c1 minus 1 on the left hand side, on the right hand side it is 0. So what you can do is a1 you have to find out, and b1 is minus 2, so minus 2, then minus 3c1, minus 3 into minus 1, so that is plus 3, then into minus 1 is equal to 0. Okay, and what you can get is a1 then plus 3 minus 2 minus 1. So ultimately you will get a1 will be 0 then. Okay, so this is it. So a1 is 0. Right. Now we'll try to incorporate these indices in the pi term. So what is the first pi term? Pi 1 is equal to d raised to a1. See, in the same order you have to take, so you should not mix up these variables now. The order cannot be changed. D raised to a1, v raised to b1, d raised to a1, b raised to b1, c raised to c1, sorry, rho raised to c1, and into delta p. To incorporate a1, b1, c1 here, substitute a1, b1, c1, just now we found out. So that is d raised to, what is d raised to a1, a1 is 0. And what is v raised to b1, b1 is minus 2. And rho raised to c1, c1 is minus 1. Then into delta p. See? So any number raised to 0 is unity. So d raised to 0 is 1. So what remains is delta p. So being the negative indices, they can be brought down to the denominator. So what will happen? Rho raised to minus 1, when it is taken to the denominator, it will become rho raised to plus 1. And v raised to minus 2, when you take it to the denominator, it will become v square, v raised to plus 2. So the first pi term is obtained. It's very simple. Delta p by rho v square. So delta p by rho v square. See, this is the first pi term. That's very important for us. Similarly, you find the other pi term. Similarly, by equating the powers of m, l, and t in each of the pi terms, see, after substituting these variables by the respective dimension. The second one I'm going to do, I'm not going to do that one for you now, because you can do by yourself. The dimensions have been listed here on the right hand side, and the left hand side, see, here we have pi 2, pi 3, and pi 4. And pi 2 dimensionless, so m raised to 0, l raised to 0, t raised to 0. Then d raised to a2, that is d has the dimension l, so l raised to a2. Then v has the dimension l t raised to minus 1 whole raised to b2. Then rho has the dimension m l raised to minus 3, that whole raised to c2. Then into l, L has the dimension L itself. So after writing down the dimensions of the various variables here in this formulated pi term, you equate the powers of ml and t, just like this one, as we have done in the case of first pi term. So you will get similarly, you can get the indices A2, B2, C2. Then A3, B3, C3 by equating the dimensions, equating the powers of ml and t on the pi term 3, okay, on both sides. And similarly, the fourth pi term, A4, B4, C4 can be found out. So this similar procedure, you please follow the similar procedure and obtain the other indices. Obtain what? Obtain A2, B2, C2 and get the term pi 2. Then A3, B3, C3, the numerical values of these indices. So that can fetch you pi 3. And similarly, A4, B4 and C4. So you will get the fourth pi term pi 4. Okay, so obtain these. So now I'm going to give you the solution straight away. So the second pi term, so similarly, the second pi term, when you find out, so it will be L by D, simply L by D, because the other terms will vanish. So what do you understand from this? The indices of the other variables, like because D, B, rho and L, D, B, rho and L involved in the second pi term, and D raised to A2, so A2 will get -1 and B2 will be 0 and C2 also will be 0, then into L. So what ultimately remains is L by D. So L by D ratio, that is a very prominent one in the pipe flow context. So this is the second pi term, L by D. Okay, so please do that by yourself. And similarly, pi 3, equating the powers of MLT on both sides after inserting dimensions in the pi term pi 3, then pi 3 you will get as mu divided by rho B D. I'm giving you the answers. Okay, so you can verify, you must verify and make sure that you get the same. Okay, and then the fourth pi term pi 4, that is just like the second one. Fourth pi term is also a very simple term, that is K, that is relative roughness, pipe roughness, K divided by D, K by D ratio. Okay, so K by D, so that will be the fourth pi term. So our solution is almost over. So if you incorporate all this and write down a mathematical relation, you will get it. See, if you monitor this first pi term very closely, if you examine that, you will find that delta P by rho V square, it is one of the prominent non-dimensional numbers you have studied already. So that is Euler's number. So, and during that narration, I told you that Euler's number is extremely important in pipeline flow cases. And obviously here you got a pipeline flow, turbulent flow through pipe, and Euler's number is going to be important. Pressurized flow situation. So the pressure force is dominant. So Euler's number is important. And now the formulation, the final part of it, the functional relationship. How do you write? It is pi 1 is a function of, see, initially I have written down these values. See over here, the problem can be from equation 2. This either you can write a function of all the pi terms is equal to 0, right hand side is 0, or the given physical phenomenon can be stated like first pi term is a function of the rest. Okay, I'm going to use the second one now. See this one, this relation number 2, and inserting the dimensions and formulate a mathematical relationship among the non-dimensional groups we have found out just now. So pi 1 is a function of, say, another function. Say I used phi 1 as a function of, so phi 1 of function of, see, I'm not going to use f of, like, because Darcy's coefficient of friction we have to use, that's why. So function of, so phi 1 of the pi term pi 2 and pi 3 and pi 4. Please be very careful about writing down these relations. Final one, because We have found out the pi terms already. What is pi 1? It is delta P, the pressure drop, delta P over the length of the pipeline, L, delta P by rho V square. Okay. And the right hand side is a function of, so you just write down pi 1, pi 2. So what is pi 2? That is L by D ratio. And what is pi 3? That is mu divided by rho V D. And the fourth pi term, it is pipe roughness K, relative roughness K by diameter of the pipe. See this. In fact, this is the answer to the question, but we have to get Darcy's equation. You have to go further and identify the other ratios as well. So mu by, see the third pi term is mu by rho Vd. See, this number is familiar to you already, because if you take the reciprocal, this is actually 1 by the Reynolds number. 1 by Reynolds number. So the non-dimensional nature of the number will not be affected if you take reciprocal, or if you take square, if you take square root or cube root, etc. Then the non-dimensional nature of the functional group will not be affected. So in that way, you can manipulate this functional group. Only thing is that you have to, every time you change the non-dimensional group, what you should do is you should write another function of another function. Here it is pi 1 of. See this. I didn't write here pi 1. Okay, pi 1 of. So if you want to do the reverse, then that is a strategy. Okay. Then if you take independent, some slight manipulations I'm going to use. See this delta P is equal to, see this delta P relation. So the time is almost over. Please bear with me for 1 or 2 minutes more. So delta P is equal to rho V square on the right hand side into function of pi 1. So I'll wind up in a minute. L by D, then mu by rho mu divided by rho V D, and then K by D. Some manipulations without affecting the functional nature of these non-dimensional groups obtained. So rho V square, and what essentially the researchers found, L by D is independent of this. So L by D can be taken out. So that is important. L by D, not always. This is from the experimental observations. So L by D can be taken out. But the moment you take this out, you have to use another function of, say another function of, so phi 2 of. And then one more manipulation I want to do. So I want to do the reciprocal, write down the reciprocal of Reynolds number. So it is rho V D by mu. So that is Reynolds number reciprocal. And the relative roughness, the pipe roughness is K by D. The K by D, that is, relative roughness. Okay. So that K pipe roughness by the diameter. So you can write like this. So what essentially you get now is a function of this Reynolds number, the last part. See the last part, if you do some manipulation, what you can find is this phi 2, this is actually a function of a Reynolds number and the relative roughness, say some epsilon r. And this part, now this is our Darcy's friction factor we want to introduce. And before that, delta P on the left hand side, see, let me write like this, delta P, and you divide both sides because we want to write frictional head loss. So the pressure intensity must be changed to the head drop. So divide by rho G. So then what you can get is delta P by rho G on the left hand side. And the right hand side, you have rho V square by rho G. Rho will be cancelled. So you'll get V square by G. Okay. And then L by D is there already. Then another, into function of this term, Reynolds number and relative roughness. Okay. Then now what remains is delta P by rho G, that is the head loss due to friction. So this is head loss due to friction. That is equal to, now, V square by V square into L. So L V square by G into D. See that functional part, this is Darcy's friction factor by 2 from the experimental observations, FF by 2. So what you can get is essentially final answer is the friction factor FF then into L V squared divided by 2GD. 2GD. What is FF? F suffix F is Darcy's friction factor, not function. Darcy's friction factor. Okay, and which usually for our equation, Darcy's equation, we used to write Darcy's coefficient of friction. That is 4 times Darcy's coefficient of friction. So this is FF is like that. So when you use this relation, FF is equal to 4 times F. So what you can get is our final relation HF. So that okay, and then so it is 2G and diameter 2G into diameter D. So 2GD. So this is the equation, Darcy's equation. Finally, by using Buckingham Spy theorem, by obtaining the functional relationship involved in this physical phenomenon, you may be in a position to arrive at Darcy-Weisbach equation. That is the final answer to the question. Okay, the functional. We found out the prominent dimensionless group and also ultimately the Darcy's equation. And how it leads to Darcy's equation, you have to practice well. Okay, then. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.